So there's a wide range of viscous versus non-viscous materials. Typically, we would call something like pitch to be a pretty viscous material. In fact, we'd usually just call it a solid. But within the range of fluids, you can have very, very viscous things like pitch, which takes many, many years to flow. And then we can also have things that are basically have zero viscosity. We'll see that a little bit later. I'll show you something that has zero viscosity, which is supercooled helium. It has some pretty cool effects when you have zero viscosity. All right, so the third thing is viscous versus non-viscous. And there are two more, compressible versus incompressible. Number 4. When we're talking about an ideal fluid flow, we're going to have an incompressible fluid. And we talked about this, but let me just sort of remind you. I'll let you remind me. Liquids are blank. Gases are which of these? Is it compressible, compressible? So option A is going to be compressible, compressible. Liquids are compressible, gases are compressible. Is it B, compressible, incompressible? I'm just going to write C and I. C is going to be incompressible, compressible, and D is incompressible, incompressible. So which of those pairs of answers describing liquids and gases is correct? Liquids are either compressible, here, or incompressible, here or here, and then likewise gases are compressible or incompressible. All right, I'll stop at 45, say. We said this earlier before the break, but I think that you can probably reason it out as well. All right, I'll stop at 50. Let's see, C is correct. C is the right answer. Liquids are incompressible. If I apply pressure to a liquid, it doesn't change the volume of the liquid. You can't compress it. That's the whole idea behind Pascal's principle and the hydraulic lift, that if you use a liquid in a hydraulic lift or a hydraulic pump or whatever, that it doesn't change volume and allows for Pascal's principle. So this is the requirement we saw before for Pascal's principle. And we'll see Pascal's principle again. So even though we had it on test 1, we could also see these things like the ideal gas law and Pascal's principle on test 2 and how they apply to the human body. But we'll see that in just a bit. All right. So liquids are incompressible, gases are compressible. And then the fifth is either laminar or turbulent. Which of these is a property of ideal fluid flow? Is it laminar or is it turbulent? Just guess if you're not sure. But which of these would you say is the ideal gas or an ideal fluid flow? Is it going to be laminar or is it turbulent? Now you've seen sort of what we've had all before. Ideal fluid flow is incompressible, it's non-viscous, it's irrotational, and it's steady. So which of these do you think it would be? Would it be laminar or turbulent that represents an ideal fluid flow? Okay, awesome. I'm going to stop at 42. 42. Okay, great. A is the right answer. Laminar just means that it all goes in straight lines. Let me give you a more technical definition. The fluid flows in parallel layers. laminar means that the fluid flows in parallel layers. This is in your book too. With no interaction between the layers. The layers near to the side of the pipe, or whatever the fluid is flowing through a pipe, say, may move more slowly. Which occurs for viscous fluids. Remember, those are the real sticky fluids. So this can occur for viscous fluids, usually at low speeds. All right, so laminar just means if I have this pipe, and I can imagine that the fluid flows in these parallel layers, and they might flow at different speeds, or they might flow all at the same speed, where we'd have, say, a high velocity out here in the middle of the stream or in the middle of the pipe, and a lower velocity on the edges of the pipe. And that can occur especially in viscous fluids. Say if you have a really thick fluid flowing through a pipe, you can get this type of laminar flow, where it's lower speed on the outer edge, but usually only at low speeds. If you have higher speeds with those viscous fluids, then you'll get more turbulent behavior. Because the higher speeds, it'll stick more to the sides and cause it to sort of curl up into this rotation and have more turbulent behavior. In turbulent flow, the layers interact unpredictably. So in turbulent flow, these layers, they'll just get all mixed up. They won't remain separate from one another. And you can get turbulent flow in the body. Sometimes blood flow is turbulent. Not always, but sometimes. Such as in the heart when it pumps. And this causes a distinctive sound. It has a name. I don't know what it is right off. Does anybody know that sound that you hear? You'll probably... What's it called? Lub dub? Is that technical, or is that just what it sounds like? Okay. Cool. That's kind of cool, isn't it? Do you tell people that? If I knew that, man, I'd be telling everybody I know. You know that sound that your heart makes? It's a lub dub. Okay, but that's because of the turbulent behavior of the fluid. That when it's engaged in this sort of turbulent behavior, it makes this distinctive sound. How do you spell it? Lub dub, as it's spelled. Two B's? No. Okay. And when you have laminar flow, you don't get that sort of sound. The reason that it occurs when the heart pumps is because you have this high velocity viscous fluid that's going through, and at these high velocities, your laminar flow turns turbulent. Okay. All right. Let's define flow rate. On the next test, you'll see some equations that you have on your equation sheet. but you'll need to know how those equations affect different things, how the variables interact with one another. Sort of like what we had on this test, but a little bit different. We'll see some sample problems. Flow rate, when we talk about a fluid, the flow rate is a measure of our volume per unit time. It says that if I have a fluid that's flowing past a given point, what amount of volume goes past that point in a given time. So fluid going past a point. The flow rate, which we usually call Q, describes what volume passes in a given time, what volume of fluid. So as you could probably imagine, our units for this, if we're looking at a volume which is going to be in, cubic meters or cubic centimeters or whatever system you happen to be in, we'll use cubic meters, our volume, and our time, of course, is in seconds. So our flow rate is going to be measured in units of cubic meters per second. We can also think of our flow rate, if we look at this, Q is equal to volume divided by time. We can also think of it in terms of area. So our volume can be described as the area times a length divided by our time. So what I'm doing here, if I have a cylinder, which blood vessels are cylinders basically, that my area of one end, this is my cross-sectional area, times my length, L here, that is equal to my volume. And the reason I do this is I can take this volume per unit time and change it into an area times length divided by time. Length over time, what does that give us? What quantity is that? Distance over time. That's our speed, our velocity, right? So this flow rate is usually expressed not as volume divided by time, but as area times velocity. And that's just an easier thing to measure, that it's easier to measure the cross-sectional area and the velocity of a fluid at a particular point than it is to measure the amount of volume that passes in a given time. So usually our flow rate is this area times velocity. Because of conservation of matter, that is to say that you can't destroy or create this fluid as it's traveling through a system. Now, if you have a system that's losing fluid or bringing on fluid, then this isn't going to be true. But as long as the total amount of matter that we have is the same, that it doesn't change, it's conserved, the flow rate must be the same in all parts of the system. All right, so for example, my amount or my volume per unit time has to always be the same, but that doesn't necessarily mean that my speed is going to be the same throughout the entire system. We see that in the circulatory system, that we have different speeds, but that the flow rate is still always the same. We'll see some pictures of that. You've probably already read about it in your book. This gives rise to the equation of continuity. Well, first, before I write the equation, let me just show you a picture. So let's say that I have a pipe that starts out big. It has a certain cross-sectional area. I'll call this big A. And down here, I'll call this little a. That's just the cross-sectional area of that pipe. And then I also have a speed. I'll call this V1. and I'll call this V2. Actually, I'm going to call this A1 and A2 as well. So my flow rate in both of these sections of pipe have to be the same. In which section of pipe is it going to travel the faster speed? Is it going to travel faster here on the left side or on the right side? It's going to travel faster on the right side because the product of the velocity and the area, that always has to remain constant. As long as I don't have any fluid that's being lost or any fluid that's being introduced, the flow rate always has to remain constant. All right? So the product of A1 V1 has to equal to the product of A2 V2 because the flow rate must be the same in all parts of the system. This is called the equation of continuity. We all use it, right? You ever use a water hose? When you put your finger over the end of your water hose? Ever done that? Like when you're washing the car, squirting your siblings or whatever. You'll do that? Well, when you put your thumb over the end of your water hose, what are you doing to the water hose? What are you changing? I change the area, right. So I cause the area to go down when I put my thumb over it, and that causes the speed to go up. So if my area, as it does here, goes down, then that means that my speed goes up. All right? Let's try a quick little question. Let's say that this area is 2 meters squared, and this area is 1 meter squared, not drawn to scale. Let's say that this speed is 4 meters per second. I want to know what is this speed. Is it going to be A, 4 meters per second? B, 8 meters per second? C, 2 meters per second? D, 1? Or E, 16 meters per second? What is going to be the speed, V2, in this pipe? I'm going from a 2 square meter to a 1 square meter here. 2 square meters to 1 square meters. Here it's 4 meters per second. What is it here? What is V2 at this point? What is the speed of my fluid in that thinner one? Okay, good. Doing really well. Just a few more seconds. If you're not certain, just ask. Well, you could ask anybody, I guess. All right. I'll stop at 42. 42. Okay, awesome. B is the right answer. Uh, the speed is going to go up, so I can get rid of this one, and this one, because I know that the speed has to go up when it goes from here to here, because it's going to a smaller area. And so in order to get the same volume flow rate, going from this point to this point, my fluid has to go faster through here. It's going to go up by whatever amount the area goes down. So here my area goes from 2 to 1, so it's decreased by a factor of a half. That means my speed is going to be increased by a factor of 2. But if you just want to do the math, you could say A1 times V1, that's 2 times 4, is equal to A2, that's 1 times V2, so 8 equals V2. All right, so it is 8 meters per second is the new flow rate. All right, let's see. Why does a gingerbread man never go to the beach? Because he's got crummy legs. All right, so let's see. Let's go back to viscosity a little bit. Different materials have different viscosities. Also, temperatures can affect viscosity. So different materials, like for example, Jello has a higher viscosity than maple syrup, which has a higher viscosity than water, which has a higher viscosity than, say, gas or air. Jello, the syrup, the water, to say air or some other gas. Those would be from high viscosity to low viscosity. And obviously the pitch has a very high viscosity. In fact, you might not even call it a fluid. I'd probably call it a solid. Um, Temperature can also affect viscosity. Usually what? Colder or warmer is a more viscous liquid. A colder or warmer liquid, right? Usually a colder liquid is more viscous. We'll see that that's not always true, but almost always it is. That usually colder is more viscous. And the viscosity will affect the flow of your liquid. It will affect the fluid flow. Viscous fluids will always need a pressure differential to flow. Viscous fluids will always need a change in pressure you can sort of think about this in terms of like Newton versus Aristotelian views, right? That if I have something and I push it and it's on a frictionless surface, it's just going to keep going forever. But if I have friction, which remember, viscosity is really just friction between the molecules. If I have friction, if I push something through a pipe, a viscous fluid, it's going to flow for a little bit, but then because of the friction between the molecules, it'll slow down and eventually come to a stop. Okay, so you can think of this a lot like we did with friction acting on bodies. That viscous fluids, because of the friction that's acting within the molecules, that eventually, unless you have this constant force or constant pressure, remember pressure is just force per unit area, so I can think of that in terms of a force. Unless I have this constant force, it's not going to flow continually. On the other hand, non-viscous fluids do not need a change in pressure. Right, so a non-viscous fluid, that is where no friction is acting between the molecules, that fluid will just flow and it'll continue to flow forever until something stops it. So that's very much like our hockey puck on an icy surface where you have no friction. Similarly, for a non-viscous fluid, it will continue to flow without a force acting upon it. So again, you can think of this in terms of friction. Because I have friction in a viscous fluid, and no friction in terms of our non-viscous fluids. If that helps you to remember that, it sort of connects it to what we've already done. Superfluids, these are kind of cool. This wasn't in your book, I'm pretty sure, but it's really neat. A superfluid is a fluid that you cool down to such a low temperature. Now, usually low temperatures will cause an increase in viscosity, but in this case, most cases that's true, but in this case, when we get to such a low temperature, that's just, I don't know, millikelvin or microkelvin above absolute zero. You're familiar when I say absolute zero, what that means? Absolute zero is the point when the point of lowest temperature. It is the point when you have a substance when all things stop moving. all the atoms stop moving, the electrons stop moving. It's a theoretical limit. You can't really reach absolute zero because you can't stop the motion of the electrons. But you can get pretty darn close with, say, liquid nitrogen and then also liquid helium. You can get down to micro or even nanokelvin, very, very small temperatures. So superfluids will travel when they are at such low temperature. Superfluids will have zero viscosity. At low temperatures. Which are near absolute zero. When you have a superfluid, there is absolutely no friction between the atoms. Or between the atoms and their container. All right, think about friction as being something that causes us to have a container. But if I were to sit on this desk and if there was no friction between the molecules in me and the molecules in the desk, what would happen to me? If there was no frictional forces between them, now there are other things at work here, but if there was no friction, what would happen to me sitting on the desk? If there was literally no friction at all, how would I fall? I wouldn't just slide off, though that might happen. But even cooler than that, what would have happened? Any idea? You're right, I would fall, but how would I fall? Huh? Not slowly. I would fall straight through the desk. It would be like the desk wasn't even there. So when I talk about with a superfluid, that there's no viscosity between the fluid, we're going to look at cooled helium, between the fluid and the container, that means like the container is not even really there. It sort of gets into this quantum effect where the material actually tunnels through. We call it quantum tunneling, where it tunnels through the material, but it's like it's not even there. I mean, you can think of it in terms of viscosity. There's no friction between the fluid and the container, so the fluid just goes straight through the container. It's like it's not even there. Isn't that cool? Let me show you a little video about it. It's pretty neat, actually. Another reason that you can never actually get down to absolute zero is because we'll talk about this a little bit later when we get into our chapter on temperature and stuff like that. But the way that we cool things is by having things that are colder, right? Like if I have a block that say, no need to write this down, but if I have a block that's say at 10 degrees Celsius and I want to make it colder, then I'm going to put it up next to a block that's at say 5 degrees Celsius, and then they'll come to some equilibrium temperature that'll be less than 10 degrees Celsius. We'll talk about that when we get into sort of the laws of thermodynamics later, in a later chapter. And so if absolute zero is the absolute zero temperature that you can have, then you can't have anything that's at a lower temperature to change its temperature. I think that this would be cool if you're at, at McDonald's and you ordered your Newton burger or whatever with cheese, and you get a Coke in a cup, and something's wrong with the Coke, like the bottom is out or something, and the Coke is dripping out the bottom of the cup. Then you could take it up to the counter, and you could say, apparently you've given me a superfluid in this cup because it's just passing straight through the bottom of the cup. Let's see what they say to you. I think that they would be impressed. Maybe not. All right. All right, let's see. Let's do a few questions. We'll just sort of look back at some of the old tests, just sort of make sure that we're all on the same page here. Let's try this number 31. Our flow rate, which is delta V over delta T, is which of these units? Is it meters cubed per second, meter seconds, meters per second, or meters per second squared? Which of those have the units for the flow rate? All right, I'll stop at 28. 28. Okay, awesome. A is the right answer. It's a volume per unit time. Volume is in cubic meters, time is in seconds. And remember also that we can think of this not as just volume per time, but as area times speed, or area times speed, and that's going to be meters squared, meters per second, and that's also going to be meters cubed per second. Let's try next one. Water flows V through a pipe whose cross-sectional area of A. If the area of the pipe decreases to A over 2, what is the new speed of the pipe of the water? Is it V over 2, V, 2V, or 4V? All right, awesome. 2 more seconds. I'll stop at, say, 28. 28. Awesome. C is right. When I get smaller area by a certain amount, the speed goes up by that same amount. So C is the right answer. Let's try this one. When the heart contracts, blood flows quickly from one region to another, causing a distinctive sound. What type of flow causes this? Is it laminar flow, rotational flow, turbulent flow, or viscous flow? This is our lub-dub. Right. All right, I'll stop at 35, 35. Killing these things. Awesome. C is right. So this pony walks into a bar and he says to the bartender, "Hey, can I have a drink?" And the bartender says, "What?" And the pony says, "Can I have a drink?" And the bartender says, "What?" And the pony says, "Oh, I'm sorry. I'm just a little hoarse." Let's try one more. When you inhale, your chest cavity gets wet. This causes a what pressure? Does your chest cavity, when you inhale, does it get bigger or smaller? And does that give you a bigger pressure in your lungs or a smaller pressure in your lungs than outside your body? It's when you inhale. If you need to demonstrate to yourself, you can inhale right. What happens to your chest cavity? And then what happens to the pressure? We talked about this last week. But think about the ideal gas law, in particular Boyle's law, which you mentioned last time. We'll see again probably next time. All right, I'll stop at 45, 45. Okay, B is right. When I inhale, that causes my chest cavity to get bigger. And because of Boyle's law, remember, PV is constant. Boyle's law was combined with Charles's law to create the ideal gas law. But Boyle's law says that this in a closed container that PV is constant, and so when I increase V, that causes the pressure to go down. Then I have a low pressure inside my lungs, a high pressure outside my body, and that causes the air to go into my lungs. When I exhale, I make that chest cavity smaller with the muscles in my chest, my diaphragm. I make it smaller, and that causes, if V goes down, that means the pressure goes up. I have high pressure inside my lungs, lower pressure outside. That causes you to exhale. All right? Let me show you one more thing. Just have a few more minutes left. But it's the Poiseuille equation. Poiseuille's equation, or Poiseuille's law. One question on your test will just be to pronounce phys. Can you pronounce it for me right now? Phys, right? It's French, I think. Poiseuille's law describes the flow rate. Remember, that's Q in terms of several variables: pi r to the fourth, p over 8 eta. This is your Greek letter eta times L. Let me just. Pi, of course, is just a number. R is the radius of the cube or whatever you're talking about. P is our pressure. In fact, we should have a delta P right here. Delta P is pressure differential, or a change in pressure, if you want to think of it in that way. It's same words, but just, or same meaning, just different words. That is, I have a low pressure over here, a high pressure over here, and so the fluid's going to go in this direction. What is that difference in the pressure? Delta P. Eta is a description of our viscosity. So, for example, syrup with a big eta, water, low eta. So this is just a constant. It's different for different fluids. If you have a really viscous fluid like syrup, you're going to have a big viscosity, eta. If we're going to have a low viscosity like water, then we'll have a low value for that. And then L is the length of your tube. You're not going to have to calculate the flow rate in any way. Like, I'm not going to say, here's all these things, and now you need to calculate the flow rate. But you do need to know how these things change. So, for example, if I have a tube that's a certain length and it has a certain flow rate, let's say that I have a tube that is 1 meter long, and I have a flow rate Q, say 4 cubic meters per second, and then I make my tube twice as long, so that now my length is 2 meters. What is going to be my new flow rate? Is it going to be A, 4 cubic meters per second? Is it going to be B, 2 cubic meters per second? Or is it going to be C, 8 cubic meters per second? Which of those is it going to be? You need to know, if I change one of these variables, how does it change the flow rate? So if I change the length by a factor of 2, what's it going to do to my flow rate? Will it cause it to stay the same, go down by a factor of 2, or go up by a factor of 2? It was 4. Well, let's say 4, 2, or 8 cubic meters per second. I'll write our equation here. Q is all right, I'll stop at 45, 45. Sorry. Okay, let's see. Oh, shoot. There we go. Let's see, y'all are sort of split between B and C. If I double the length, so if I put a factor of 2 over here in the length, I increase that by a factor of 2. In order to balance this equation, in order to not change it, I have to put a factor of a half over here. So whereas my Q was 4 cubic meters per second, now it's going to be what? It's going to be 2. It's not going to increase, it's actually going to go down. And that sort of makes intuitive sense. If I have a hose and water flowing through it at a certain rate, if I make the hose twice as long, you wouldn't expect it to flow through twice as fast. It would flow through at a slower rate. All right, let's imagine that this will be our last one. Instead of making it longer, let's say we keep it the same length. But let's say now, let's say the radius is 1 meter, and then I make the radius to 2 meters. All right. Is it going to be A, 4 meters per second cubed, B, 16 meters per second cubed, C, 32 meters per second cubed, D, 64. Make sure I'm getting this right. RE, oh shoot, I'll just tell you. I'm sorry. So here, if I double R in this case, that means I'm going to have a 2 to the 4th. So I'm going to have 16 times over here. So which would it be? It was 4. Now it's going to be what? 40 plus. It's what going to be what? It's going to be D, right. So D would be the right answer. If I have, because I have that R to the 4th. We'll come back to the Poiseuille equation next time, and we'll sort of see some more questions. But you'll have that type of question on the test. How are these things related to the various variables? You have all those equations on your equation sheet. Just make sure that you're familiar with them. You know where they are and what they describe. You have a great day, okay? I'll see you on Tuesday. Wait, can y'all hold on just a sec? Tuesday. Okay, yeah. We're not going to, definitely won't have the quiz on Tuesday. We're not going to have it on Thursday. Let's go ahead and plan that quiz, the Chapter 3 reading quiz, for that following Tuesday. That's a week from this Tuesday.